Okay, we are going to talk about carboxylic acids. This is chapter 17 in either version of the book. Chapter 17 is all about carboxylic acids. The outline that we're going to follow is here. We're going to begin by talking about the structure and properties of carboxylic acids. We're going to move on to nomenclature, how to name them. We're going to talk about several different ways to synthesize carboxylic acids. And actually, we already know most of these, all but one of them. And then the meat of the chapter is all about the various reactions of carboxylic acids. And there are a number of them. So one of them that we're going to learn in great detail is so-called Fischer esterification. This is a reaction where we convert a carboxylic acid into an ester, which is going to be a new functional group for us, so I'll introduce that to you. Then there's a very specific reaction involving diazomethane, which also produces an ester. It will turn out to be a methyl ester. We're going to talk about how to form amides from carboxylic acids, and even how to form acid chlorides, which you've already seen. If you remember Friedel-Crafts acylation reactions, they use acid chlorides, and now finally we're going to learn how to make them from carboxylic acids. And then we'll wrap up our study of the reactions of carboxylic acids by talking about a very unique one involving the reaction with two equivalents of an organolithium species in order to produce a ketone. Finally, after we finish all that discussion of reactions of carboxylic acids, we're going to end by discussing something that is important in our everyday lives, and that is soaps. And it turns out that there's a number of soaps that are made by a number of different people on a small scale, on a large scale. Traditional soaps that may have been made on farms, for example, back in the day before you could purchase soaps in a store. And these days, the sort of soaps that are sold as all natural products, usually at a hefty price, they are actually long-chain fatty acids, where fatty acids refers to a carboxylic acid. And they're made via a saponification process, saponification of esters. So we're going to talk a little bit about that. So that's our topic. Carboxylic acid. So we begin with the first of those bullets, which is structure and properties. Well, as far as the structure is concerned, the carboxylic acid is not going to be unusual to you at all, because you've already been studying carbonyl derivatives, for example, aldehydes and ketones. So you're used to seeing this carbonyl group, a carbon doubly bound to an oxygen. And you know that it's a pretty stable arrangement of atoms. That pi bond with the carbonyl group is actually a very strong pi bond, as pi bonds go. With a carboxylic acid, rather than having a hydrogen attached to the carbonyl carbon, that would be an aldehyde, or another organic group, R group of some sort, that would be a ketone, instead we have a hydroxy group, an OH. And so the carboxylic acid group in total has this structure right here. That is the carboxylic acid group. It is the most highly oxidized form of carbon that we can have on an organic molecule. Notice that this carbon atom is attached to, or I should say, has 3 bonds to oxygen, 2 to this one and 1 to that oxygen. 3 bonds to oxygen. The only more highly oxidized carbon species would be carbon dioxide, CO2, which is a combustion product. So if we burned organic compounds, we could get a more highly oxidized carbon. But short of burning, this is as highly oxidized as they get. Carboxylic acids are present everywhere. They're present in nature, in all sorts of different locations. They're very important species in organic chemistry. The carbon atom, as you know from your studies of aldehydes and ketones, where you have seen carbonyl carbons before, the carbon atom is sp2 hybridized, which means it's trigonal planar, and so the oxygens and the first carbon of that R group are all lying in a plane, and I'm showing them in the plane of the board here. So it's pretty standard as far as structure is concerned. And I would say that as far as properties are concerned, there won't be any surprises either. They are, after all, called carboxylic acids, so it shouldn't be a surprise that they have some acidity. And in fact, we've talked about this in class before. The simplest of the carboxylic acids would be acetic acid. At least this is one of the simplest carboxylic acids. Acetic acid right there. And acetic acid is the common acidic ingredient in vinegar, for example. So if you've consumed salad dressings in your lifetime, then you've definitely consumed a lot of carboxylic acid. What is it that is acidic on the carboxylic acid? It's that proton right there, that proton that's on the hydroxyl group. Now if this were an alcohol, so if somehow we got rid of that carbonyl, turned this into a methylene, and now we just had a regular old alcohol molecule, I guess this one would be ethanol, that proton is not very acidic. We don't think of alcohols as being acidic. They are actually slightly acidic, but only very, very slightly. Once you put that carbonyl group on board and you have this carboxylic acid function, that proton becomes much more acidic. These things are organic acids. They're not as strongly acidic as sulfonic acids, which you learned how to make in the electrophilic aromatic substitution chapter. They're not nearly as strong as sulfonic acids, as it turns out, but they're still relatively acidic, certainly one of the more acidic organic functionalities. So what would happen if we brought along a base? Let's just be very generic about it. I'll say B for base, it could be anything. But if it's a good base, it's going to have a lone pair available and maybe a negative charge. And this lone pair is going to come and pick up that acidic proton. The aeroformalism would look like this. The base picks up the acidic proton. It is delivered as a proton, as H+, as the other half of this aeroformalism indicates. And look what's left behind. First of all, we have our conjugate acid. Since I started with B-, when it picks up a proton, it would just be BH. This would be the conjugate acid of that base, whatever it is. But over here, our carboxylic acid is deprotonated, and we have this conjugate base. This conjugate base, being derived from a carboxylic acid, is going to be resonance delocalized. So I can kick that lone pair, any of those lone pairs, in to form a new pi bond, while simultaneously bumping those pi electrons out onto the oxygen above. And the result is I can draw a new resonance form in which I now have the negative charge at the other oxygen atom. And it's actually this resonance, these two resonance forms, which help to explain why carboxylic acids are so much more acidic than alcohols. When you deprotonate an alcohol, the OH group of an alcohol, you form an alkoxide that is not resonance delocalized. But when you deprotonate the hydroxyl group of a carboxylic acid function, it is a resonance delocalized conjugate base. We refer to this particular species, this resonance delocalized conjugate base, as a carboxylate anion. Carboxylate anions are very typically formed in situations where you have a carboxylic acid in the presence of a basic species. We're going to see carboxylate anions in several places moving forward. So there you have it, the structure of the carboxylic acid dominated by the sp2 character of the carbon and the trigonal planar nature of the atoms around that carbon, and the properties, namely the acidity of carboxylic acids. What sort of bases will deprotonate them? Well, because carboxylic acids are reasonably strong acids, as organic acids go anyway, it isn't going to take a terribly strong base. So you can deprotonate carboxylic acids in water, for example. Water is not a very strong base, but it's basic enough to deprotonate the relatively acidic carboxylic acids. That's going to produce the resonance delocalized carboxylate anions. So there's structure and properties. We've covered that. Let's move on to nomenclature. How are we going to name these compounds? Well, as we've been learning, as we move on in organic chemistry, there's not just one naming convention for a lot of these carbonyl-containing compounds. You might remember that with ketones, for example, it was possible to name them in at least two different ways. The same is going to be true for carboxylic acids, and we're going to name them according to what is easiest. So for example, if you just had a regular old alkyl chain attached to a carboxylic acid, it's very clear that the molecule is going to terminate with a carboxylic acid because you see carboxylic acid functional group doesn't contain bonds to carbon on both sides like a ketone does. It basically terminates with the carboxylic acid. So for that reason, it's going to be relatively easy to name this thing. We would number it in such a way as to give the carbonyl carbon of the carboxylic acid the lowest possible number. So 1, 2, 3, 4, 5. And the way we would name it is we would start with the base alkane, which in this case would be pentane. And we would subtract the E. So we're going to subtract off the E, and then we're going to add oic acid. And that will eventually be 2 words. So we're going to add the phrase oic acid. So the base alkane is pentane minus the E plus oic acid, and this becomes pentanoic acid, which needs to be properly spelled. And yes, there is a space in between those 2 words. So it's 2 separate words. Pentanoic acid. And then if you had some number of methyl groups or other alkyl groups or halogens on board, you would treat it exactly as you would expect. So for example, you choose a longer chain now. There's my carboxylic acid. And I'm going to go ahead and put a methyl group right here. And I'll go ahead and put a bromine right there. Well, now I've got these 2 stereogenic centers, one here and one there. I need to determine the absolute configuration at each of those. So in the case of the carbon bearing the bromine would be the highest ranking group, followed by this side over here, because as I work out atom by atom, this carbon on the left is only bound to 1 other carbon, whereas this carbon is bound to 2 other carbons. So it's going to be bromine to this side over here to the ethyl group. The group of lowest priority, the hydrogen, is already located in the back. It wasn't shown, but I'll put it in there now. And so this is a counterclockwise rotation with the group of lowest priority in the back. The absolute configuration is S. Over here, as I work out atom by atom, I have carbon, carbon, and carbon. It's a tie, but the methyl group can only go to hydrogen. This carbon can only go to another carbon. This carbon can go to a bromine. So it's going to be this side, followed by this side, followed by the methyl group. This is once again a counterclockwise rotation with the group of lowest priority, the hydrogen in the back. I won't draw it in there this time. And so both of those stereogenic centers happen to be S. So I would go ahead and name this by first numbering this longest chain. This is going to be a heptanoic acid, heptane minus the E plus oic acid, a heptanoic acid, but it's going to be a bromomethyl. So we've got a 5 bromo, 4 methyl, heptanoic acid. Since I have those 2 stereogenic centers, I've got to include that information in there. It is a 4s, 5s configuration. So we include that in the normal way. So naming these carboxylic acids when they're just part of a straight alkyl chain is pretty simple. Now, what do you do, though, when it's not part of a straight linear chain like that? For example, what if it's just on a ring? So here's a carboxylic acid group which is present on a cyclohexane. Now in this case, you could try to use the same convention. Instead of calling it cyclohexane, you call it cyclohexanoic acid, except that you see there's a problem with that because this carbon of the carboxylic acid is not part of the 6-membered ring. So it doesn't really work. And in fact, the carboxylic acid can't be part of the 6-membered ring because that wouldn't allow for all of the bonds. What am I trying to say here? If I try to put the carboxylic acid actually into the ring, I can get a carbonyl group in there, but I can't draw the OH because I'd be in violation of the octet rule, too many bonds at carbon. So there won't be any carboxylic acids that could be named cyclohexanoic acid. That's an impossible structure, as it turns out. So what do we have? We have a cyclohexane and it's attached to a carboxylic acid. And so the way we would name it in this case is to call it cyclohexane carboxylic acid. Which sounds kind of clunky, I suppose, but it's the best option in a case like this. Cyclohexane carboxylic acid. And of course, there are also going to be some trivial or historic names which are quite prevalent. We know that that is always the case in organic chemistry. I've told you about this compound already. This is a benzene ring attached to a carboxylic acid group, and it is called benzoic acid. This is the one that, for those of you that are taking the lab, you probably did a melting point experiment at some point early in the first semester lab. And benzoic acid is a solid white crystalline material, fairly easy to crystallize and to get a nice sharp melting point on. So it's typically featured in a melting point experiment in labs. So we've got multiple different cases here. There's one more situation that deserves a little bit of discussion, and that is the case where there's actually two carboxylic acids on the molecule. Turns out that these compounds are also fairly common. So take a look at this molecule. It is a hexyl group, 1, 2, 3, 4, 5, 6, and it didn't really matter if I numbered from the right or the left in this case, because there's symmetry in the structure. And think about how you might name that. Think about that for a second. You can't really call it a hexanoic acid because that doesn't tell you that you've got two carboxylic acids on there. It's a diacid, so the name's going to have some sort of an indication of two acids on there. And in this particular case, the way you would name it is to revert to this alternative naming mechanism that we used for the cyclohexane carboxylic acid. We would just call it a hexane, but rather than a hexane carboxylic acid, since there's two of them, hexane dicarboxylic acid, or perhaps a preferred name would be hexane dioic acid, excuse me. Hexane dioic acid or hexane dicarboxylic acid, both of those would be acceptable. The names get a little bit clunky with these carboxylic acids just because of the nature of them and the fact that there are going to be multiple examples like this one where you can't use a nice smooth oic acid ending. Nonetheless, you should be aware of the fact that these molecules that have two carboxylic acids are actually very, very common, as I mentioned, and they're utilized extensively in the polymer industry. This particular diacid, for example, this dicarboxylic acid spread over 6 carbons, is a precursor to nylon. So you can imagine why these things would form polymers. You've got a reactive functionality at one end of the molecule and a reactive functionality at the other end of the molecule. And if you react them with another bifunctional compound, you can just continue to get reaction at both ends, which grows in both directions. Pretty soon from a small molecule into an oligomer and eventually into a polymer. So this is actually a precursor to nylon, which is a very common and well-known polymeric material. So we've covered nomenclature, we've covered structure and properties, and now it's time to turn our attention to syntheses. How do we actually synthesize carboxylic acids? I'm going to talk about 3 syntheses. 2 of them you've already covered. So very recently, you learned about the oxidation of alcohols and aldehydes to carboxylic acids, and we're going to review that. Going all the way back into the first semester of organic chemistry, you learned an ozonolysis reaction. This is a reaction of an alkene. Ozonolysis of an alkene, if it's accompanied by an oxidative workup, can, in certain cases, give rise to carboxylic acids, and so we'll review that. And then finally, the third reaction is going to be a new one. This is going to be a reaction involving an organometallic species. You know about organometallics. We've covered them in a lot of different reactions. But we're going to allow those organometallics to react with carbon dioxide. And notice the little S here in parentheses. That stands for solid. So solid carbon dioxide. Solid carbon dioxide is also known as dry ice. And you've probably seen or maybe even worked with dry ice in the past. If you've ever been to a concert or some sort of a performance on a stage and you see fog all over the floor, that no doubt is the result of dry ice which has been dropped into water and it starts to sublime and you get that fog. Okay, so on to syntheses. Syntheses of carboxylic acids. And as I said, we're going to begin with the oxidation of either alcohols, primary alcohols that is, or aldehydes. So, oxidation means, can be shortcut, O in brackets, oxidation of primary alcohols and or aldehydes. Let's look at an example. Here I have 1-butanol. 1-butanol can be oxidized in a whole bunch of different ways. This is very recent chemistry that we learned. One of those ways is to hit it with a very powerful oxidant like a potassium dichromate in the presence of sulfuric acid. This is a powerful oxidant, and what will happen, as we've recently discussed, is that the 1-butanol will initially be converted into the aldehyde. That is an oxidation reaction because I'm increasing the number of carbon-oxygen bonds from 1 to 2, while simultaneously decreasing the number of carbon-hydrogen bonds from 2 to 1. So this is truly an oxidation, but what we learned is that because we're in sulfuric acid, even though it's not always indicated in our description of the reagents there, because we're in sulfuric acid, there's going to be lots of water around. And one of the reactions we learned involving aldehydes and ketones is that when there's water around under acidic conditions, it will be in equilibrium with the gemdiol, the hydrate. You hydrate aldehydes and ketones under these conditions. I'll just write H+/H2O, which is exactly what you've got here. Sulfuric acid's going to have water around. So you're going to form this gemdiol, and this gemdiol is actually the species which is responsible for the over-oxidation. It will just continue all the way to the corresponding carboxylic acid. So even though you may have wanted to stop at the aldehyde stage, if there's water and acid around, you won't be able to do it under these oxidizing conditions in the presence of potassium dichromate. You'll form the gemdiol at equilibrium. It'll probably only be formed to a small extent at equilibrium, but that's enough. Once it's formed, it will be oxidized, and then Le Chatelier's principle will produce more of it, and it continues to oxidize, etc., 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 until you've got all of your primary alcohol converted into the carboxylic acid. The truth of the matter is, this is the sort of reaction, I'll just change it up a little bit here. We've got 1, 2, 3, 4, 5, 6. So this is now a primary alcohol with 6 carbons, a 1-hexanol. The truth of the matter is you can get a reaction like this to occur, that is the over-oxidation of a primary alcohol all the way to the 6-carbon carboxylic acid, using a whole host of oxidants. So the one I showed up there, potassium dichromate, sulfuric acid certainly works, but potassium permanganate, which we know is a strong oxidant, and we've utilized it in a couple of different times in our course, is going to do the same thing. Potassium permanganate would be an aqueous solution. So once again, the problem is going to be that you're going to form some geminal diol, which will over-oxidize. Nitric acid. We don't always think of nitric acid as an oxidant, but it actually is a very powerful acid, a Bronsted acid, which is also a very powerful oxidant. And again, it's a mineral acid. There's going to be lots of water in it. So it's the same story. You're going to oxidize first to the aldehyde, then to the gem diol. You'll form the gem diol and it will over-oxidize. You'll end up making the carboxylic acid. Or as we said, you could just use the potassium dichromate in the presence of sulfuric acid. Bottom line is, if you have a primary alcohol and you're trying to oxidize it, you better be careful because it's very easy to over-oxidize all the way to the carboxylic acid. Carboxylic acids are the topic of this discussion, so we're really emphasizing this as a useful reaction. What if you wanted to stop at the aldehyde stage, though? What if you wanted to oxidize the alcohol and stop at the aldehyde and not allow it to over-oxidize? Well then, as we've recently discussed, you're going to have to use some dry conditions like PCC, pyridinium dichromate, or perhaps just chromium trioxide and dry pyridine. And we've discussed those reactions recently, so hopefully you remember those. But for today, we want to make the carboxylic acid, so we're going to hit it with one of these aqueous, strong oxidizing acid systems. Okay, so that's method number one, oxidation of alcohols. We've also got on here oxidation of aldehydes, and I hope it's no surprise to you, given the discussion we just had, that aldehydes will do exactly the same thing under these similar conditions. So for example, if you took any aldehyde, I'll just go ahead and choose benzaldehyde, but this is applicable to any aldehyde at all, and you treated it to any of these conditions which we just described for primary alcohols, what's going to happen is that you will over-oxidize to the corresponding carboxylic acid. And in this case, since we started with benzaldehyde, we would produce benzoic acid. How does it happen? Well, all of these are aqueous acid systems. Under those conditions, you're going to form the gem diol. Aldehydes form them rather rapidly under those conditions. And it is the gem diol which will oxidize to the carboxylic acid. So it's really the same discussion repeated again. So there it is. Primary alcohols and aldehydes are very easy to oxidize to carboxylic acids. I probably should have written here primary alcohols, because secondary alcohols and tertiary alcohols won't do it. Let's look carefully at a secondary alcohol and a tertiary alcohol to understand why that is true. If I move to a secondary alcohol like isopropanol, and I try to oxidize it under one of those sets of conditions, perhaps it's the potassium dichromate in the presence of sulfuric acid. Well, I can oxidize this thing, but it will oxidize to the ketone first. And although the ketone can also form a gem diol under these conditions, and no doubt would form a gem diol, the thing that's different is that there's no bond to hydrogen here. There's no possibility to continue the oxidation. Remember, we refer to an oxidation as a loss in the number of bonds to hydrogen and or a gain in the number of bonds to oxygen. Well, I've got 2 bonds to oxygen there. I've got 2 bonds to oxygen here, and no hydrogens that I can lose. I can't add an additional bond to oxygen or remove an additional bond to hydrogen at this carbon because there's no more bonds to hydrogen to lose. So ketones basically will secondary alcohols will simply oxidize to give ketones, and although they are in equilibrium with gem diols under these conditions, the equilibrium dramatically favors the ketone side, and for the most part we don't even recognize that those gem diols are there in very, very small percentages. From a synthetic perspective, we would just say the secondary alcohol oxidizes to give the ketone. Likewise, if you have a tertiary alcohol, look at that tertiary carbon right there. It does not have a single bond to a hydrogen atom. This secondary alcohol here had 1 bond to hydrogen, so it could oxidize once to the ketone. The primary alcohol, which I've erased but I'll put back on here, had 2 bonds to hydrogen, so it could oxidize twice all the way to the carboxylic acid. Secondary alcohol has just 1 bond to hydrogen, it can only go to the ketone. The tertiary alcohol doesn't have any bonds to hydrogen, it can't oxidize at all. if you try to form a carbon-oxygen double bond there, you're clearly going to be in violation of the octet rule. That carbon would have 5 bonds. So this tertiary alcohol is not even going to react under oxidation conditions. It's not going to form an oxidation product. Okay, so that takes care of the synthesis of carboxylic acid using a simple oxidation of primary alcohols or aldehydes. Let's move on now to the ozonolysis reaction. It's been a while since we've talked about ozonolysis. This is a reaction that goes all the way back to the first semester. Hopefully you'll remember it, and I think once we go over it you will. In an ozonolysis reaction, I'll just give you a simple example here. You start with an alkene, and the alkene we're going to treat with ozone in the first step. Ozone is O3. In the second step, if you go back to your notes from Organic Chemistry 1, you recognize that we can actually do a workup in one of 2 different ways. We can either do an oxidative or a reductive workup. Now, for the purposes of forming carboxylic acids, we're going to be interested in an oxidative workup, which means we're going to use H2O2. What happens in the ozonolysis reaction is that you chop the alkene in half, break it apart into 2 pieces, and wherever there used to be a carbon-carbon double bond, you put a carbon-oxygen double bond. So when you do that, when you karate chop this thing in half, break it into 2 pieces, you've got this sort of a species here. Now in this particular case, because I had such a highly substituted alkene, I don't form any carboxylic acid at all. I form 2 ketones. But if I change the alkene just ever so slightly, let me put one of those bonds emanating from the alkene carbon here to hydrogen rather than to a methyl group. Now, if I perform the exact same reaction, ozonolysis in the first step, followed by an oxidative workup, I'm going to chop that alkene in half, break it apart. Wherever I had a carbon-carbon double bond, I'm going to place a carbon-oxygen double bond. I'm still going to form 1 equivalent of acetone, like I formed 2 equivalents up there. But on this side, look what I would form. I would form an aldehyde. But the aldehyde, in the presence of hydrogen peroxide, which once again is going to be an aqueous oxidant solution, will be in equilibrium with the gemdiol once again. And the gemdiol will oxidize under these conditions to go to the carboxylic acid. So you'd make, in this case, 1 equivalent of acetic acid plus 1 equivalent of acetone. These would be your 2 products right here. Acetic acid here, acetone there. When we talked about this in the first semester, I didn't go into this detail about telling you why the aldehyde overoxidizes, that it passes through this gemdiol. The gemdiol then has this oxidizable hydrogen right here, which can be lost to give you a carboxylic acid. But now we recognize that that is indeed the case. One more example for you. Speaking of hexane dioic acid, which I told you was an important precursor to various polymers, you can actually form it in an ozonolysis reaction using cyclohexene. So if we take cyclohexene and in the first step treat it with ozone, followed by an oxidative workup, in this case we're going to chop that alkene in half, and when we pull it apart, we have a couple of aldehydes, both of which will over-oxidize under these conditions to form carboxylic acids. So you can show it this way if it helps you to visualize from where it came. Here I've chopped that alkene in half, pulled it apart, inserted my carbon-oxygen double bonds. They over-oxidize to the carboxylic acid. But really the better way to show this is to say it's a 6-carbon system, 1, 2, 3, 4, 5, 6, with carboxylic acids at either end. There's our hexane dioic acid again. So, we can prepare carboxylic acids from the ozonolysis reaction. And you've known that for quite a while, but now it comes full circle because we understand and appreciate a few more things about carboxylic acids compared to where we were back in the first semester. now, let's talk about a new reaction, this one right here. The reaction of organometallics with carbon dioxide, solid carbon dioxide, or dry ice. As far as organometallics are concerned, you were introduced to two of them quite a while ago, and we've used them extensively. One are the so-called Grignard reagents. And the other is the so-called organolithium. And the R's can be just about anything here. Now, both of them have in common that the carbon of this R group is attached directly to a metal, and the metal is very electropositive. The electropositive metal is basically going to allow for this sort of a resonance form to be quite reasonable. We're going to take both electrons of this polar covalent bond and put them onto the R group, which gives the R a negative charge and the magnesium a positive charge, and that's the state that magnesium would like to be in, being a metal. And it really emphasizes the fact that the R group, the organic portion of the organometallic, is quite a good nucleophile. It's nucleophilic. It looks like a nucleophile. It's got a lone pair and a negative charge. I can do the exact same thing with the organolithium. And there's that nucleophilic look in this particular resonance form for the organolithium. Well, that's exactly the way these things behave. We've seen this, for example, recently when we looked at the addition of either Grignard reagents or organolithiums to aldehydes and ketones, for example. Now what we're going to do is we're going to add them not to an aldehyde or a ketone, but instead to solid carbon dioxide, CO2, dry ice. Here's how it would go. Let me start with a phenyl magnesium bromide. There's my Grignard reagent. I've just sort of arbitrarily decided I'm going to work with a Grignard reagent. By the way, how would you make this? Just so you don't completely forget, the way you do this is you would start with the corresponding halide, which in this case would be a bromobenzene or a phenyl bromide, and you would treat this with magnesium metal. Magnesium metal is denoted with a naught or a 0 there. And the solvent, in the case of Grignard reagent formation, is very important. You need an ether. So magnesium metal in the presence of an ether will convert the bromide into the Grignard reagent, in this case the phenyl magnesium bromide. How would you have made the phenyl bromide? Well, that could have been made from benzene using bromination conditions. So now we have enough knowledge, enough reaction knowledge to start with benzene and to produce this phenyl magnesium bromide. That's going to be the starting point for our reaction here today. We're going to allow this to react with solid carbon dioxide, dry ice. Carbon dioxide looks like that. It's a very interesting molecule. It's like two carbonyls in one. Both of the carbonyl groups are part of that same carbon. You can tell by the linear structure that this carbon in the middle is actually sp hybridized. So it's linear like an alkyne. Also looks a bit like an accumulated diene, which we talked about some time ago. Well, anyway, the carbonyl carbon, this doubly carbonyl carbon, is going to be a good electrophile, just like all carbonyl carbons are. And here I have a nucleophile. Now, I'm not going to resort to that other resonance form for my aeroformalism. I'm just going to take advantage of the fact that I appreciate that those two electrons right there of that polar covalent bond essentially mostly belong to the carbon. And so I'm going to take those two electrons and I'm going to attack the carbonyl carbon of dry ice. Now when I do that, I've got to have to break one of these pi bonds, otherwise I'd be in violation of the octet rule. So I'm going to go ahead and break this pi bond up top. You could just as easily have broken the one on the bottom. What's the result? The result is, number one, this is going to be pretty much an irreversible reaction, like a lot of reactions of organometallics. It's irreversible. My benzene ring, my phenyl substituent, is no longer going to be attached to the magnesium bromide. When I take those two electrons, I'm taking them as part of that carbon because that carbon really owns those electrons much more so than the metal. And so what's left behind is just a magnesium cation, a counter cation, a spectator ion, which is just now floating around and watching. The carbon took the 2 electrons, there they are right there, and attacked the dry ice, and we showed this pi bond breaking, and so there it is. The pi bond has broken, and what's left is that other carbonyl. It's still there. And you realize what this really is just a carboxylate anion. And there's the spectator ion, the magnesium bromide cation, which is just floating around watching. So this is kind of drawn, this functional group is kind of drawn upside down, but just appreciate the fact that you can spin it around the other direction, and this is just equal to this view of the carboxylate anion. Looks very much like any old carboxylate anion. This one happens to have a phenyl substituent on it. So that's how you do it. You add dry ice to an organometallic. That would be the first step. In a separate second step, we're going to add some water and some H3O+. There's 2 reasons to do this. One is you want to quench any of the unreacted organometallic, which is either a Grignard reagent or a phenolithium. You're going to quench it with the water. And secondly, you're going to protonate under these acidic conditions that carboxylate anion such that you get the neutral carboxylic acid product, which would be this one right here. Benzoic acid in this case. So that's how we can produce carboxylic acids through a reaction with dry ice. Well, if you understand that, then you should be able to solve the following synthesis problem. I want you to start with this 4-carbon alkene, 1, 2, 3, 4. This would be a 1-butene. And I want you to derive 1, 2, 3, 4, 5-carbon carboxylic acid from it. So you should stop the video right now, you, not me, stop the video right now and work on this. And when you turn it back on again, I'll show you exactly how to do this. Okay, we're back live. And now we're going to look at how to synthesize this 5-carbon carboxylic acid from this 4-carbon alkene. First thing you want to notice is that there's an extra carbon here. And whenever you see an extra carbon and you've made a carboxylic acid, you should be very suspicious of this reaction we just studied, which is the reaction of dry ice. Because in the reaction of dry ice, we're going to add CO2, dry ice, as an extra carbon. So in other words, what I'm saying, if we want to think about this retrosynthetically, is that this thing could very easily have been made from a 4-carbon organometallic, let's say a 4-carbon organolithium, plus dry ice in the first step. There it is, solid CO2. That would be the first step, followed by, let me show it this way. This is the retrosynthetic arrow, so this came from that. In the forward direction, it would be CO2, solid, reacting with that organolithium, and in the second step, H2O, H3O plus quench to give me that carboxylic acid. So that would be a nice way to produce the carboxylic acid starting from this 4-carbon organolithium. Now where would that come from? Here's my retrosynthetic arrow again. That could come from something like a 4-carbon alkyl halide, and I'm going to choose a bromide for a reason that will become obvious in just a moment. How would you do that? Well, if you don't remember how to make an organolithium from the corresponding bromide, it's pretty simple. You just need 2 equivalents of lithium metal. In this particular reaction, the solvent is a little bit less critical than it is in the Grignard case. You don't necessarily have to use an ether. You could use several other solvents. So we're not going to specify the solvent here. Well, from the bromide, I can produce the organolithium, which I can react with solid ice, or solid CO2, or dry ice, followed by a water H3O plus quench to give me my product. But I'm not supposed to start with that bromide. I'm supposed to start with this alkene, and actually, I know how to do that. The reason I've chosen the bromide rather than, let's say, a chloride or an iodide is there is a particular reaction which will allow me to convert an alkene like this into a bromide like that. This is an anti-Markovnikov hydrobromination. The bromine is added to the less substituted carbon. How do I do that? I do that using HBr, under free radical conditions, which might look something like this, HBr in the presence of a free radical initiator like a peroxide and a little bit of light. I've now defined the synthesis. I'll sort of shortcut it over here so that you can see it entirely in a forward direction. HBr, peroxide, and some lighter heat will give me the anti-Markovnikov 1-bromobutane, which can then be converted to the corresponding 4-carbon organolithium, which can then be reacted in a first step with solid CO2, and in a second step H2O, H3O plus, to give me a 5-carbon carboxylic acid. This is the step right here where I go from 4 carbons to 5 carbons, and it's the solid CO2, the dry ice, that allows me to do it. So there's my synthesis. It's a 3-step synthesis, 4 if you count that quench step as a separate step, of that carboxylic acid. Pretty straightforward. So moving over here, what have we done so far today? We have looked at the structure and properties of carboxylic acids. We've learned how to name them, and we've discovered 3 different, very distinct ways to produce them. This last way, the reaction with organometallics, being a new reaction for us. Well, we're down to reactions of carboxylic acids. There are several reactions here to go over, and we're going to go over them one at a time. The first one, the Fischer esterification, is a very important, they're all important, but the Fischer esterification is a very important reaction. Once we learn the Fischer esterification, we are going to use it over and over again, repeatedly. Because, as it turns out, it's a very convenient way to convert carboxylic acids into esters. As the name would imply, Fischer esterification is going to produce esters. Esterification, making esters. The reaction, I'm going to show you the overall reaction first, would look like this. We're going to start with a carboxylic acid. And what we're going to do is we're going to react that with an alcohol. And in order to distinguish my R groups here, I'm giving the alcohol an R prime. These R's and R primes could be the same or they could be completely different. It really doesn't matter. But to distinguish them, I'm going to call that R prime, whereas my carboxylic acid just has R. This is an acid-catalyzed reaction, and it is completely reversible. So I need an equilibrium arrow there to imply it's reversible. And I need the little H plus to indicate it's acid-catalyzed. How would you do this? Usually you use sulfuric acid, so you just dribble in a couple drops of sulfuric acid into your solution. Now what's going to happen is that you're going to convert this carboxylic acid into the ester. And so let's look at an ester. An ester looks a whole lot like a carboxylic acid. Here's our acid. Here's our alcohol. And we're about to draw an ester. I haven't drawn the last thing on there yet, but look at it. The carboxylic acid and the ester look exactly the same. The only difference is the acid terminates in a hydrogen, and the ester is going to terminate in something organic. It's going to be that R prime right there. That's my ester. The other product, if you're keeping track of all the elements and what's missing, is water. So this reaction has a lot in common with some of those reversible reactions of aldehydes and ketones that we talked about not too long ago. It's one of those totally reversible equilibrium situations where a product is water. In order to drive this equilibrium to ester, in other words, in order to make a large amount of ester, I'm going to have to get rid of the water. I'm going to have to pull that off one way or another. We talked about removing water using molecular sieves, or a Dean-Stark trap, or some other method. One way or the other, by Le Chatelier's principle, I can drive this thing towards formation of ester if I can just get rid of the water as it's formed. And that's not too terribly difficult to do. Another way, though, that you can drive this toward ester is just to bulk up on the amount of alcohol you use. So in other words, if you start out with some quantity of acid under acid-catalyzed conditions and you just use a large excess of alcohol, that will drive the equilibrium toward ester. That's also very commonly done. If for some reason you wanted to take the ester and produce carboxylic acid, you can do that as well. Now you just load up the system with water, and that will drive the equilibrium in the opposite direction, in this case toward the acid. So this is the Fischer esterification. Now I want to point out that although esters and carboxylic acids look a lot alike, they are very different in many ways. The carboxylic acid is acidic. The ester is not. The ester doesn't have that hydrogen right where the acid does. So an ester is not an acid at all. But even other properties are very different. For example, low molecular weight carboxylic acids like propanoic acid and butanoic acids and pentanoic acids, they're actually very horrific smelling compounds. The odor associated with these compounds is really bad. In fact, it's an odor that you've probably smelled, unfortunately, because if you've ever smelled rancid butter or milk, or if you've ever had things like sweat socks stuck in a locker for 6 months on a hot summer or hot fall and summer seasons, and you pulled out those sweat socks and you smelled them, and that horrible smell you associate with something like that, that's all the result of low molecular weight carboxylic acids, which in the case of the sweat socks are produced by bacteria. And in fact, in the case of the rancid butter and milk, it's also low molecular weight carboxylic acids that are produced by bacteria. So those low molecular weight carboxylic acids really do not smell good at all. Now, move over to the esters. So structurally similar. This hydrogen has just been replaced by an R group. These are the most fragrant and beautiful smelling organic compounds there are. In fact, there are a lot of organic chemists that work in the fragrance industry. They make perfumes, they make colognes, they make fragrances for a variety of purposes. The vast majority of those fragrances are esters. The natural products you associate with very fragrant aromas, like for example, if you go out into your garden in the summertime and you have some flowers that are in bloom and they give off a nice, beautiful aroma, that is no doubt the result of an ester, which is produced naturally in the plant. Other things, the odors you associate with certain fruits and vegetables, like bananas, the oil in bananas that give bananas their fairly pleasant odor, is in fact an ester. So esters and carboxylic acids, very similar looking but very different set of properties all the way around. Esters, a very, very important functional group in organic chemistry. Get used to looking at this collection of atoms right here, and